Okay, so I'm hearing lots of questions. I saw a fair bit of questions on the quiz about a lot of like, why do orbitals do this sort of questions, which is a very fair thing to ask. And I don't like to say just trust me or just memorize that these are the rules. So I'm not going to expect you to do anything with this, but hopefully this will make some of the logic behind those quantum numbers make sense. All right, so does anybody remember what the quantum numbers were? I mean, I guess I never fully defined them anyway. There was basically N is our energy level, is our first energy level. That's called the primary quantum number. Then there were these other three quantum numbers. L, which was basically orbital type. Its actual name is the azimuthal quantum number. But it's basically what's the shape of the orbital. So like S or P or D. And then there's two others. There's M sub L, which is basically what piece of a p orbital is it in. So like a p orbital has three different lines that go along with it, right? Which is why it holds 6 electrons in the p block. The M sub L is basically which of those three different pieces of the p orbital does the electron go into. So they're all the same energy, but it kind of just says, is it along the x-axis, is it along the y-axis, is it along the z-axis? They call that's called the angular momentum quantum number. And then there's M sub S, which was spin, and it can be either plus 1/2 or minus 1/2, but those are the only two values. It can be either spin up with a plus, or it can be spin down. Right, so this all looks really, really confusing and hard to navigate. Like, what do we do with any of this? But we've already been doing it by drawing in those orbital diagrams. Right, if I looked at the electron configuration for carbon, there's 1s, there's 2s, and then there's 2p. We'd be fill in all the electrons. So it looked like that, right? That has all four of these quantum numbers. The 1 or the 2 is your energy level, is your principal quantum number. Is it an S or is it a P? Is this quantum number, is the azimuthal quantum number, it's the orbital type. M sub L is always the same value for an s orbital because there's only one place to put electrons in an s orbital. It's always, the value for M sub L is always a 0. But p orbitals could be 1, 2, or 3. So this third quantum number is just which one of these is it in. And then last but not least, the spin is just, did I draw the arrow up or down? So all of this information is in this diagram. But why do we have to follow the certain rules? Why does a p orbital get 3 pieces? How come that the n equals 1 doesn't have a p orbital? It all has to do with this equation called the Schrodinger equation, which is, it is the same Schrodinger's cat thought experiment. Basically, if you have one electron surrounding a nucleus, you can calculate the energy levels. What are the exact energies of these different states, these different orbitals, by using this function. This is one version of the Schrodinger equation that it's fairly complicated, involves lots of derivatives, lots of constants, lots of other random stuff. And there's this other function R that fits into there as well. And there's L. N is actually buried inside of R, as are the two M values. Basically, your quantum numbers are just a set of values that allow this function to work properly. Right? I compared it to a parabola, trying to find the roots of a parabola that doesn't cross the x-axis, right? The quadratic equation gives you a non-real answer if you try to solve it for a parabola that doesn't cross the x-axis. You get a non-real number if you try to plug in stuff that doesn't follow our rules. for quantum mechanics. If you try to plug in n equals 1.5, the function doesn't work. You get basically a divide by zero error at some point in the process of this. And it's actually a little more specific than that, but it's like a divide by zero error. It's not even like you get an imaginary number. You get a number that can't exist. And then we get the same. So n can be any integer, technically. N can be 1, 2, 3, so on. What's the highest n value that we have for any of the elements we've discovered? 7, right? We've only gone up to the 7th row of the periodic table. So basically, we know that n, for most of the systems we're looking at, n can be anything from 1 to 7, but it has to be an integer. It has to be discrete, to use the math term for it. L is basically, an L can be anything from 0 to n minus 1. If you're going to put a number to it, we usually describe the orbitals as letters, S, P, D, F. But technically, if we're plugging them into this function, we would use 0 would be an S orbital, 1 would be a P orbital, 2 would be a D orbital. And you're limited. If you try to plug in an L value that's too big, if you try to calculate the energy for a P orbital in n equals 1, again, you get the function just doesn't work. You can't do that. And it's really, it seems like weird that the universe would be so picky about numbers at such a small scale, but for whatever reason, it's just sort of the boundary conditions of the universe. When you get really, really small, then they have to follow these rules because of the Heisenberg uncertainty principle and because of the way that these electrons behave as waves. And our rules for this one, we can actually predict what are the size of the different orbitals beyond just looking at the periodic table. Your M sub L, basically, which is, again, is which of these different pieces, suborbitals, is your electron in. You can have anything from negative L all the way to 0 to positive L. When, again, it has to be integers. So if L is 0, because we're talking about an s orbital, how many different suborbitals could we have? Well, if L is 0, the only possible value for M sub L is also 0, right? Alice? Alice here? There you are. What happens when L is 1? If we're talking about a p orbital, L is 1, right? Which means we get 3 possible values for M sub L. Our 3 possible values would be negative 1, 0, and positive 1. So if we wanted to, we could actually label these as minus 1, 0, and plus 1. So basically, this rule tells you how big each orbital can be. An s orbital can only fit 2 electrons. A p orbital can have 3 suborbitals, so it can fit a total of 6 electrons. So basically, the number of electrons you can fit into each orbital goes up by 2 times odd integers. Because every time L goes up, we get 2 more suborbitals. So that's why a d orbital holds 5. Or it has 5 suborbitals, so it can hold 10. Excuse me. And an f orbital has 7 suborbitals, so it can hold 14. Somebody's question on the quiz was, do they stop at f orbitals? Not according to the math, because if we go to n equals 5, we have 5 different suborbital types: S, P, D, F, and G. You'll notice that there's no G block on the periodic table. Basically, it's just too high energy. For the elements that we're able to make so far, we don't observe anything that actually has a measurable G orbital. we can calculate it, and we can actually take some of the lower energy electrons and bump them into a g orbital. But it's a really unstable situation, and we don't see it in nature. Yeah.
It's just plasma at that point.
It gets trickier because you probably actually need to have it as a gas in order to prevent other atoms from interacting with it. So I think you'd probably only see it in the gas state.
I know with like supernovas and stuff like that, it creates new elements from the original ones.
Mm-hmm.
Do you think if our sun like went through that, it would create elements we haven't discovered yet, or would it discover ones that we have?
So based on our best guesses at this point, making those last elements in that island of stability would actually take more energy than a supernova can provide. Basically, the conditions on a supernova, there's more total energy in a supernova, but it's not concentrated enough in order to get there. Yeah.
Okay.
So basically, that's why none of them show up in nature anywhere we've been able to see, and even in other solar systems or anything like that, we haven't seen evidence of those really super heavy elements, because we basically need a more concentrated way to put the energy. All right. So again, I'm not going to ask you to go through these rules for each of these, or even come up with the names, other than maybe the principal quantum number. We should know what that one means. In general, I just wanted to give some more clarification as to why those rules for drawing these electron diagrams work the way they do. And it's because of this function, Schrodinger's equation, and the fact that we're limited to only certain values will actually allow that equation to be true. Which means this is the equation that's basically describing reality. And so if only certain values make this equation true, it means that those electrons can only exist at those certain energy levels. Which makes things really interesting when we do something like move an electron from one energy level to another. Because even though, so for carbon, for instance, carbon's got electrons in the 2p orbital, it still has a 3s orbital. It's just empty. Which means if we supply the right amount of energy, we can actually move one of these electrons up to that higher energy level. Right? And there was one slide on it, but it was before some of the other quantum stuff, so you might have forgotten it. What did we use to move electrons from low energy to high energy? Any guesses? Light. You shine light on it. In order to move an electron from a low energy level to a higher energy level, the easiest way to do that is to shine light. The trick with that is that it has to be the right energy of light. There's a specific change in energy. Everybody's familiar with using delta for change, right? We've been using that. I'm not mixing up this class with the only other class, am I? We talked about delta yet? No. Okay. Thank you for shaking your heads. So delta is just scientific shorthand, meaning change in something. So you can have delta anything, and it literally just means, mathematically means you take your final minus your initial. So in this case, delta energy would be our final energy minus our initial energy would be delta E. But you can have delta T for temperature. You can have, you can have all sorts of, anytime you have something changing, delta is a useful shorthand. So when you see that, you just draw it like a triangle. Olivia? Gloria. I keep calling, your middle name's Olive, right?
Yeah.
That's why I keep doing that. Sorry, Gloria. Say that again. This would be change in energy. This would be what we actually plug in. If we're trying to move an electron up, we say that's final energy. This is our initial energy. So our change in energy would be final minus initial. All right, so if we're trying to move an electron up, we can't just shine any light on it. It has to be light that has the right frequency so that one photon of that light has that same amount of energy. Which is why some dyes and some things will absorb certain colors but not others. Because there has to be an electron transition with the right delta E in order for a material to absorb light. Why some things are colorless, but they're opaque in the IR. For instance, like glass. Glass is colorless and transparent when you in the visible region, in the UV region. But if you look at glass in infrared, it actually absorbs a lot of different wavelengths of infrared because it has certain in the case of glass, it's a vibrational transition, not an electronic transition. But the point remains, you have to be able to absorb the light in order to do that. Yeah. It's clear. It's partly. There's two different things happening with water. It does absorb in the IR region, in the infrared region, but it also scatters light in the visible region. So it's more that it's just sort of scattering the light than it is actually absorbing things in the visible region. It absorbs light at certain IR frequencies around 3,000 wave numbers. We take OCHEM, we can talk about why that is. The other thing that this idea though that you can have this gap and have it absorb energy to move an electron up, that's actually how solar cells work. Photovoltaic literally means light turned to voltage. Photovoltaics are built out of a material that has a gap between their energy levels. When you shine the right wavelength of light on it, you can bump an electron to the higher energy level, and they're wired cleverly in such a way that once you move an electron to that higher energy level, instead of just letting it fall back down, you basically force it to go through a water wheel. And in order for it to fall back down in energy, you have to run it through a circuit first, and you can capture energy by doing that, by using that energy to charge a battery or something like that, or power a light bulb. And if you flip that in reverse, you use a battery to move an electron up and then let it fall down naturally. You create a photon of that same wavelength, of that same frequency. So that's how LEDs work. An LED is literally a photovoltaic wired differently. Right? We have different requirements for them, so we use different materials for them. But in theory, that's the only difference is, are you using voltage to promote an electron, or are you promoting an electron using light and then capturing that energy? All right, let me make sure that I did. So I addressed these second two. How do electron detectors work? I thought that was a good question. Electron detectors work just as the simplest version is actually exactly what we were just talking about. Old versions of TVs and computer monitors called cathode ray tubes, right? We learned about cathode ray tubes when we first learned about where electrons came from. So the earliest versions of an electron detector would basically, you coat the inside of a piece of glass with this stuff called a phosphor. And a phosphor, basically, if an electron hit it, it would absorb that electron and it would glow for a second. And so earliest TVs just did that. They just used electron guns, basically, to they did some fancy math with the signal coming in over the air to turn it into this different waves. And then it would take that wave and put it through a transform that would basically create a magnetic field so that some electrons would go that way and some electrons would go that way. And if you do that really well and you're really clever with your engineering, you can actually create a picture doing that. But that's really all the inside of that glass, curved glass, is that phosphor that'll just light up when an electron hits it. So you can just visually see it when an electron hits, and then it basically, the glow goes away. It runs out of energy.
Like older box televisions with the like protruding screen, that's why.
Yeah. And it was protruding, one, because you couldn't have air inside that tube, or else the air molecules would get in the way of the electrons. The electrons would be flying through, and then that would make your picture fuzzy or not work at all. And so that they're called vacuum tubes. Those vacuum tubes had to be a vacuum, or else it didn't work, which is why if you've ever broken one of those, they kind of implode. The curved glass is pretty thick, and it has to be curved to withstand the pressure from the air on the outside to keep it a vacuum on the inside. And if you get a small crack in one of those screens, basically your picture gets fuzzier. The more air molecules get in there, the fuzzier your picture would get. And that the fact that you had to be really, really clever with the engineering to get it to do that, because basically you had to do what's called a Fourier transform. The way that radio waves work and transmit information is basically you take a really long wavelength of light in the radio spectrum, and then you add another shorter energy wave on top of that. When you add both of those together, you get constructive and destructive interference, and you get something that looks like a really, really weird jagged wave. And basically what you had in the TV or in the receiver was a way to take this really jagged combination of waves and separate it back out. And that process is called a Fourier transform. When you do the Fourier transform on this wave, you get these back again, and this can carry information in it. And that can be sound, it can be light, and it can be binary information like a picture. But it takes a lot of fancy math and a lot of trial and error and building on what other people do to take this idea and turn it into a television. Quinn?
They would like keep having to do that and really got to flat screens, or did they like change it and just keep the curved screen? Like
They still did that. There was some versions that were called projector screens, where basically you had a projector pointed kind of like at the back, and then had a mirror that projected it forward on the inside. If it was like a big screen TV, it wasn't actually glass on the front. It was actually like a softer material. Those were actually usually projector TVs, where you had a projector with a lens built into the bottom. And it would project the lens onto a mirror and then onto the inside of the box. But all the glass TVs, anything that was a big square box that had a glass screen, was a CRT, cathode ray tube. The earliest computer monitor, not earliest computer monitors, all the way up until I think 2002, most computer monitors were CRTs. Until laptops were really, really expensive in the early 2000s, because they were some of the only options that weren't CRT screens. All right. Last but not least, and this does tie into this as well. What about neon? I mentioned neon. Neon's on the periodic table. Everybody's heard of neon lights, right? Neon is actually the earliest version of neon lights. Actually, was just a tube filled with neon, and then you applied a voltage to it that caused current to pass through that gas, and it glowed. So just like we were talking about here with the LEDs, it was a less efficient version because you had to apply a large enough voltage to get a current. It's basically like a very small scale version of lightning to pass through the neon gas. And when you did that, neon glows this really, really vibrant red orange. So true neon lights are always red. The ones that are white are usually either argon or xenon. And those argon and xenon ones, they glow white, and so you can just paint the outside of the glass whatever color you want it to be. But true neon lights are actually just red, which is kind of fun. And we'll do flame tests, and we'll do some practice where we actually take a color of light and use it to figure out the frequency of that light, and then use it to figure out energy transfers. If not this week, then next week. So good job asking good questions, because I think that was helpful to actually go through the why for these a little bit more, right? At least I like talking about quantum mechanics, so I don't mind. We ended with this slide the other day. We talked about zinc versus zinc ions. But let's do iodine, since iodine was on the quiz. And I think a lot of you got it right on the quiz, but the autocorrect didn't mark it correct for whatever reason. So just because you got marked down on the quiz for your electron configuration doesn't mean you actually missed it. I'm going back through and reassigning points. That just takes me a little bit of time. All right, so take a minute. If you don't have your notes from the quiz, take a minute and redo your electron configuration for iodine. We know what it's going to start with, though, right? They always start the same way. 1s2, 2s2, 2p6. That gets us the neon right there. 3s2, 3p6. Now we're fourth row, 4s2, 3d10, 4p6. That gets us to krypton, right? Yeah. So 5s2, 4d10, 5p5. All right, so we just follow our same process. It's long in this case, but it's the same process no matter what. The biggest trick to remember is that these D blocks are offset by one row, right? Some textbooks and some online resources will actually tell you to put 3D before 4s to keep all of the n equals 3 electrons together. I don't really like that because that doesn't match the periodic table, but I won't mark it wrong. If you wrote it out as 3p6, 3d10, then 4s2, I would still mark that as right. It just doesn't make as much sense to me. But that's me. You're you. You're allowed to think differently.
So which is the order the electron would actually fill in normal energy? Right?
Yeah. But once the 3D gets filled, it's actually lower in energy than the 4s.
Because it's more stable.
Because it's more stable once it gets filled up. So that's why there isn't really agreement there, because once it's filled, you get this. But until it's filled, they're switched. So if I'm just doing the zoomed in version. So if you have 4s that can hold 2 electrons and then 3d, when 3d is empty, it looks like this. You do 4s first and then 3d. Once it fills, though, this one drops in energy because it becomes more stable. And so you actually wind up with them switching. So you'd wind up with 3d and then 4s would be above that. So that's why when we're taking electrons away, we take them away from the 4s before the 3d. Because they actually do shift as you're filling them up. These we write that the molecular orbital or the atomic orbital diagram like they're fixed, because when they're empty, they're always in the same order. But as you start filling them, they shift a little bit. Right, and that also creates some other weirdness where, like, the electron configuration for iron, no, sorry, chromium. for chromium, we would expect it to be 4s2 3d4, right? But we actually get a slight bonus to our stability when we have an orbital that's exactly halfway filled. So chromium actually has this electron configuration. It's 4s1 3d5. And so, and that's because these are so close to each other and because they shift back and forth a little bit, that can happen. And that's why I'm not going to have you memorize all of the electron configurations in the D block. It's because you get weirdness like this. And it really happens only when you can get something that's exactly halfway filled. And it has to do with that magnetism. Remember, unpaired electrons with the same spin have cause magnetic fields. And so that means that's actually, you actually gain this stability by creating a magnetic field. This is more stable than putting 4s2 3d4. And it's not as important as getting as once you get a full 3d orbital, but it's similar. And so some periodic tables will actually have the electron configuration on the periodic table. In fact, I think P table has a way you can do that. P table's great. So in its default, it just looks like that. But if you can actually sort it by or have it colored by electrons, and then it'll actually show you what the electron orbitals look like with the arrows and everything. And if you look at chromium, 4s1 3d5. And we would expect molybdenum to do the same thing. And we do. 5s1 4d5. And if we go exactly halfway through the F block, off by 1. And actually you don't see the same thing in the F block because these energy levels start getting so close together. More weirdness starts happening. So again, not going to have you memorize all of those exceptions. Just know that they're there. Did I see a hand a second ago? No? Okay. All right. What about something that involves the F block? How about lead? We won't do the complete one for lead since we just did that whole process. Who's been doing their studying for the elements quiz? Everybody knew that lead was PB, right? So tip when it comes to memorizing these, at least for me, the ones that don't match up at all oftentimes have an interesting story about why they don't match up. Does anybody know why lead is PB? Potato. No, earlier than that. It actually predates European knowledge of the potato. In ancient Rome, yeah, potatoes aren't native to Europe, right? They're native to South and Central America. Yeah. So until Europeans made it to the New World, they didn't have potatoes or tomatoes, for that matter, in Europe. That's neither. Yeah. So it became a big deal for Ireland to grow potatoes instead of leeks because you could get more calories out of a potato, and so you could live hand to mouth on a potato farm easier than if you were farming leeks or other root vegetables that were native to Ireland. Anyway, PB comes from the lead word or the Latin word for lead, which is plumbum. Anybody ever done any construction? Any worked in construction? All have family works in construction. You ever heard of a plumb bob? That's literally what they used for plumb bobs originally, was just a little piece of lead. A plumb bob is just a string with a weight attached to it. So that when you hang it, you get a perfectly vertical line. So the earliest way to, instead of, if you didn't have a level, if you wanted to make a post that was straight up and down, you used a plumb bob. And a plumb bob gave lead its name. Plumbum. Potassium is K for. You asked me about one of the ones that I don't remember off the top of my head. It's also Latin. Na for sodium is the Latin is natrium. Gloria? Aurum. Aurum.
What about mercury?
I'm glad you asked about mercury because
Calcium for potassium.
Callium, Kallium. So Hg for mercury. It works better if we ask about silver first. Silver is argentum, which I think in Portuguese it's still argentum or something really close to that. So Hg, the Latin for mercury was hydroargentum, which is literally water silver. So because it was a liquid at room temperature and it was metal, they've named it liquid metal.
So for silver, I think that's why they named Argentina that way, because of Argentum, because there's a river there called Rio de la Plata.
Yeah, and plata is the Spanish word for silver, right? Yeah, that's exactly why they named that. Say it a little louder, Taylor. Yeah. No numbers. Just like if I write silver, you write Ag. If I write Au, you write gold. And it will include the F block. Yeah, all of them. But it's going to be more heavily focused on the stuff towards the top half. Out of 30, there might be 5 that are F block or lower, or like in those bottom 2 rows. Zachary? Ferrum. That's another good one. That one's not Latin. Tungsten being W is because it was discovered by 2 different research groups at the same time, one in Germany and one in the UK. And the way that they compromised, since neither one they couldn't decide who discovered it first, they were arguing about it. The compromise was that the British group got to name it, but the German group got to pick the symbol. So the German word for tungsten is Wolfram. So I think it's an O. Wolfram is the German word for tungsten out of a compromise because they were fighting about who discovered it first. See, some of those are actually decent stories, and to me at least, it helps me actually remember them better. If I didn't have some of these stories, I would have trouble with these. I like the story behind tungsten and wolfram. I think that's a really good story. So bismuth looks the coolest. I'll bring in a sample of bismuth. Bismuth is really cool, square rainbow crystal. I don't know that one off the top of my head. 74. All right. Let's bring that back to doing electron configuration for lead. We'll start with the last noble gas. We'll use that abbreviation. So for lead, it starts out as what? Xenon. Right? So that gets us all the way to 54. That saves us from having to write a whole bunch, right? And then we can say, okay, well then from xenon, we get cesium and barium. So we're in the 6s2. And then it gets a little bit tricky, right? We'll get to the 6p in a second. We got to go through the F block first. And again, the F block and the D block here wind up being really close together in energy. So sometimes there's some weirdness about what order it fills up in. So I'm only going to ask you about things where they're completely filled or completely empty. So in this case, we follow from 56, we get 54, which takes us down to the F block. So we're going to be putting electrons into the f orbital. And the first f orbital is in what energy level? 4. F. 14. And then we're into the D block,
Right, D10.
which is, and now we're in the 6th row. So that means that the D block in the 6th row belongs to n equals 5. So it's 5, D, 10, 6, P, 2. That's literally as complicated as it can get when it comes to these electron configurations. All right. Your F block is off by 2. Your D block is off by 1. And then your P block and your S block are always on the money. All right, questions about electron configurations? Exactly. So if you go from calcium to scandium, so calcium is 4s2. The next electron you're going to be putting in there is going to be in the d orbital, and it's the d orbital belongs in n equals 3. So it'd be 4s2, 3d1 for scandium. And just yeah, d block's always just off by 1 spot. Behind, yeah. Electrons, you mean?
Sorry.
Basically, is it left of that stair step line? Remember that blue stair step line is how we divide metals from non-metals. Anything left of that line is a metal, and it's going to try to give away electrons. Anything to the right of that is a non-metal. It's going to try to attract electrons.
Like calcium, like you're saying, just do 3D3 instead of 4s2, 3D1.
No, because that 4s orbital is lower in energy until the d orbital gets filled. Until you get further along. Yeah.
So you can just do abbreviations for anything after argon, right?
Anything with more than 18 electrons, you can use this abbreviation system. Yeah. Basically, if you have this written out, then you just count whatever the largest principal quantum number is. Like so we have lead written here, right? The highest energy level that has electrons is 6, right? N equals 6. And there's a total of 4 electrons in N equals 6. So we'd say that lead has 4 valence electrons. And once you get practice at it, you can look at the periodic table, you can see that. Right? Because you know that you're going to leave off the D block and the F block. And so you just basically the easiest way to count valence electrons, you just count how many columns over you have to go. And you just leave off the D block and the F block. Right? Because anything that is not in the D block or the F block, it's just how many rows or how many columns over you have to go. So for lead, if we want to know how many valence electrons it is, we'd say, okay, 1, 2, skip D and F, 3, 4. 4 valence electrons. Anything else, like if we want to, how about arsenic, AS? 1, 2, skip the D block, 3, 4, 5.
What about things like in the D block or F block?
So in the D block, assuming it follows our normal rules, that it's not one of those weird exceptions, they're all going to be 2. Right? Because 1, 2. So let's look at iron. Iron is in the middle of the D block, 4s1, 4s2, and then a whole bunch of electrons we're putting into 3d, which don't count as valence. So that means anything in the D block, we can usually assume it has 2 valence electrons. Now, really, it's a little bit more complicated than that, because if we have one of those cases like chromium, where we had the irregularity, where it was 4s1, 3d5, technically chromium only has 1 valence electron. It doesn't follow our usual rules, though. So our normal rules are count from left to right, and you just ignore the D block. And so everything in the D block, we can assume for the most part is going to be 2. Copper, silver, gold are actually 1. Chromium, molybdenum are actually 1. I actually don't know about tungsten. Tungsten might be 1 or it might be 2, because we're getting to the weirdness range when you get really far down there. Right, but the counting valence electrons is if you go to the trouble of actually writing out your electron configuration, you just find what has your highest principal quantum number, and you count all those electrons. So for iodine, it would be what? Be 7, because you've got 2 electrons in the 5s, 5 electrons in the 5p, and the d orbital doesn't count. Zachary? Same thing. F block is going to behave a lot like the D block in terms of it's because it's offset, and you're filling those s orbitals first. They're mostly going to be they're mostly going to have 2 valence electrons. All right. Any more questions about the quiz stuff? This is all good. This is what I wanted to spend this time doing, was making sure we were good on this stuff. Michaela? Not for this quiz. On the midterm, yes. On the midterm, I'll ask you to count valence electrons, write out electron dot structures, that kind of thing. Or not electron dot structures, sorry, electron configurations. Not for the quiz on Thursday. Quiz on Thursday is literally just, if I write IR, you write iridium. If I write palladium, you write PD. Just back and forth that way. Nothing to do with numbers, nothing to do with where it is on the periodic table. That's okay. Do you have another one? That's how you can tell if it's going to be a positive or a negative when it becomes more stable. Anything to the left of that line is going to try and give away electrons to become more stable. So if it gives away electrons, it actually becomes positive because the electrons are negative, right? So lead has 4 valence electrons, but it's to the left of our line there. Lead becomes more stable when it can give up all of its valence electrons. So lead is most stable as a +4. Because these ones just get left alone. Right? Iodine, on the other hand, is to the right of our line. So it's going to try and gain electrons to become more stable. And so it needs to gain 1 electron to become more stable, which makes it -1. That's right? Ish. If a reasonable person can read what you wrote and get to the right name, then, and the reason that I qualify is like, you leave out a whole syllable, I'm going to mark you down. If you leave out 1 letter, it kind of depends on what the letter is. If it's zinc and you leave out the Z, that's kind of an important letter, right? So I can't give you a hard yes or no. Get as close as you can, and I'll be gentle. Say that again. Yes. So for things like uranium would have its last electron would be 5f4, probably. All right, how are we feeling about this?
It's not super kind of relevant question. With the blue line and the like numbers, elements of 118, how does that play in?
118 doesn't last long enough for us to actually determine any of its properties, so we actually don't know how it behaves. It's too heavy to be a true noble gas because it won't be a gas.
Yeah.
But we actually can't make enough of it and have it last long enough to measure a lot of its properties. So it's kind of
Oh.
nebulous. Good question though. Yeah. So the question was, how do the arrows correspond to each block? And we're filling these in. Basically, the p block is 6 elements across because a p orbital can hold 6 electrons. Right, so if we had 2s, 2p, an s orbital, because of those rules we talked about at the beginning, can only have 1 suborbital. And that means you can hold 2 electrons in a suborbital as long as they're opposite spins, as long as one points up and the other points down. We represent that with those arrows. So the an s orbital, when it's filled, looks like that. That corresponds to 2 electrons. Right, so lithium, it has a 1s that's filled, and then it has a 2s that only has 1 electron in it. It doesn't matter if you draw it up or down, as long as you only have 1 arrow there. Because it's not filling up that whole column, that whole block. Yeah. So oxygen, we've got 4 electrons we need to put into the p orbital because oxygen's 4 steps into the p block, into the p block. So 1, 2, 3, 4. Right, and so that's what that in the shorthand would be: 1s2, 2s, 2s2, 2p4. Right, we're just all this is these, except in shorthand. Make sense? Cool. All right. How are we feeling about all this? All right. Good, because electron configuration in orbitals lays the groundwork for a ton of other properties. We're going to talk about a few of them today. What are called periodic trends. Basically, there's a lot of properties that we can predict, at least qualitatively, just by looking at where something is on the periodic table. If we understand how these orbitals work, that all makes sense. If we don't start with orbitals and electron configuration, then it's just basically memorizing. And y'all know by now I don't like that. I want to explain why it behaves that way. And then we can work on applying that. Right? So valence electrons is one of those periodic trends. And they're called periodic because they repeat every time you go through the periodic table. When you get to the end of one energy level and you start the next row, that you see a lot of repetition there, like valence electrons. Other than any irregularities, all the valence electrons are going to behave the same way as everything else in the same column. Everything in the same column as nitrogen is going to have the same number of valence electrons. Right? And so from top to bottom of a group, the different columns, the old school way of naming those was to call them the groups. Every group is going to have the same number of valence electrons. So column 2, the one that starts with beryllium, is going to have 2 valence electrons. Everything in that column will have 2 valence electrons. And again, the D block and the F block things get a little bit weird. So for the most part, I'm not going to ask you about those at this point. But anything past the D block follows that rule as well. Right? So we can look at gallium. Gallium, aluminum, and boron are all going to have the same number of valence electrons. All right, the next property that we can talk about, so that one makes a lot of sense when we talk about electron configuration in orbitals. Atomic radius is a little bit weirder. We have to think about it a little bit harder, but it's exactly what it sounds like. How big are the individual atoms? Now, in terms of energy levels, when we add electrons into more energy levels, into higher energy levels, would we expect that atom to get bigger or smaller? Right. One of the first ways we started was basically those energy levels are basically distance from the nucleus, right? So when we go from top to bottom in a column, they're going to get bigger. Lithium is bigger than hydrogen. Sodium is bigger than lithium. Because every time you go up one energy level, we're getting a little further away from the nucleus, which increases the radius. The weirdness happens when you go from left to right in the same row. When you go from left to right in the same row, things actually get smaller. Even though you're adding more electrons in there, once you get electrons into the n equals 2 energy level, adding more electrons into n equals 2 doesn't really change the size of n equals 2. N equals 2 is the same size regardless of how many electrons are in it. Just like, just because your older sibling moved back home doesn't change the footprint of your house, right? Your footprint of your house is the same regardless of how many people are living there.
How does the element get smaller?
So the element gets smaller because what else is changing when you go from left to right across the periodic table? If we're adding more protons. If we're adding more protons, what do protons do to electrons?
Oh,
They pull it all in tighter. Protons are positively charged, so as you add more protons to the nucleus, it sucks the electrons in a little bit tighter. So as you go from left to right in the same row, elements will actually get smaller. So fluorine is actually smaller than carbon, even though it's heavier. And even though it has more electrons, all of the electrons are still in the second energy level. Yeah.
Is that why usually like bigger elements are denser than like some of the items?
So again, which weirdness starts happening when you start talking about solids. If we talk about the actual individual atoms, then actually our most dense atoms are actually going to be towards the top right. They're not as heavy, but they also have fewer energy levels, so everything's pulled in a little bit tighter. But when you start involving solids, you actually have to deal with how those spheres interact with each other and how tightly they can pack as well. So you get some other weird. I think osmium is the most dense element, and that one's square in the middle of the block. So it gets kind of hard to predict that way.
Like for atoms, it's like most dense when they're like the tightest.
Yeah. Yeah, and they are going to tend to be at the right-hand side of the periodic table because as you go from left to right, everything gets pulled in tighter, and you're adding mass at the same time. Right, and you can kind of see that a little bit. And I guess not really, because the densities I know off the top of my head are lead is about 11, mercury is 13, gold is 19, osmium is like 22 grams per cubic centimeter. They don't really follow necessarily in a predictable trend, which is why we don't consider density to be a periodic trend. It's not going to be one of the ones we talk about today because it's irregular. All right, so if we think about it in terms of energy levels and remember that protons are involved as well, atomic radius kind of makes sense too. It's a little bit less obvious than counting valence electrons though. All right, so as you go from top to bottom in the same column, things get bigger. That makes sense. When you go from left to right in the same row, they get smaller. Right. So, and when I'm going to ask you questions like about this on the quiz and on the midterm, I'm going to pick the ones that I'm asking you about very carefully to make sure that you don't have those two variables competing with each other. Right. So I'll ask either about things that are in the same column, and the way that I ask questions about this would be like, rank these three from smallest to biggest. And it might be fluorine, oxygen, and sulfur. So fluorine we would expect to be smallest. And sulfur we would expect to be the biggest. Because sulfur is in the N=3 energy level. More energy levels is bigger. So if we're comparing sulfur to oxygen, we'd say sulfur is bigger than oxygen. We're comparing oxygen to fluorine. Fluorine's got more protons in the same energy level. So fluorine's going to be smaller. Right? Seems simple enough as long as I'm up here explaining it. If I give you a blank piece of paper, then and ask you to explain it to me, then that gets a little trickier. So we'll keep practicing with it. But here's some good practice right here. Which is bigger, neon or carbon? Neon's heavier, but carbon is larger, has a larger radius. Right? Because neon has more protons and electrons, but they're in the same energy level. And more protons means neon will pull the electrons in tighter. Aluminum or gallium? Which one's larger? Gallium. They're in the same column, that's easy. More energy levels means bigger. But magnesium or bromine? Now, this is one of those ones where those two variables are kind of working against each other, right? Magnesium has fewer electron orbitals or electron energy levels filled, but bromine's a lot further to the right. That's actually one that I would look up. You can't use periodic trends all the time. Sometimes you wind up with them like, I'm not quite sure. I could make the argument either way. Which the other thing that I will say about that is on my tests, if I ask you a question like that and you're not sure what the answer is because you could reason it both ways, write out your reasoning. If you write out your reasoning, I can give you partial credit. Otherwise, this is basically a true-false question. I can't really give partial credit for guessing, right? But if you say, well, I think bromine because it has more energy levels, even though it's further to the right, I can give you at least partial credit, even if you're wrong. But I'm going to try not to ask you the confusing ones like that on the test. All right, questions about atomic radius? All right. Ionization energy. Ionization energy, we have to define this before it makes any sense. All right, so don't worry about writing those down yet. Ionization energy is the energy required to remove an electron. Not just the energy to make an ion, because we're not talking about giving something an electron. We're specifically talking about we get our atomic tweezers and we pull a single electron off. How much energy does that take? So in general, if we're in the same column, as we go down that column, we're getting further and further away from the nucleus, right? We're getting further and further away from the nucleus. How tightly are those electrons going to be pulled by the protons? More tightly or less tightly? Less tightly. They're already partly out of that system. They're already, if you have an electron that's in 5s orbital, it's already a long way from the nucleus, which means it's easier to pull that off. So the elements at the bottom of the periodic table have a lower ionization energy. It's easier to pull the electrons off. So that kind of makes sense, right? What else changes when you go from left to right in the same row? Electrons and protons. In general, the further you go to the right, the more tightly those electrons are going to be held. which is why that line between metals and non-metals is where it is. Anything to the right of that line is going to get more stable by gaining electrons. And so they tend to have higher ionization energies. It's harder to pull an electron away from something that's trying to gain electrons. All the metals, it's really easy to pull an electron off. They're already trying to give electrons away. But things closer to the right-hand side of the periodic table are going to hold on to them a little bit tighter, including the noble gases. All right, so for some of these properties we're going to talk about, the noble gases are kind of an exception. We kind of ignore them because they don't really do anything anyway. But in this case, ionization energy matches as well. Once you get to being a noble gas, they're already super stable, right? They already got a full energy level. And trying to take an electron away from neon, when it's already all the way filled, we'd actually have to break up a full energy level to do that. That's not very stable. So further to the right, your ionization energy goes up. And further, closer to the top of the periodic table, your ionization energy goes up. So that top right corner, helium, neon, and fluorine, those are going to be the hardest elements to take an electron away from. They're going to have the highest ionization energy. You know, on the flip side, cesium, francium, radium, and barium, it's so easy to take an electron away. You don't actually even need to take it away. If you just have cesium metal on its own, it'll just flame electrons out into space. It does usually these things, the electrons are still at least partly bound, because even something like sodium, it's still got a positive charge in that nucleus, right? It means if you took an electron away, well, now you have a negatively charged electron and a positively charged ion. They're going to stick back together again. So most things on the periodic table, you have to have something, you have to have a place for the electron to go. Not for cesium. Cesium reacts so quickly, its ionization energy is actually negative. It's actually, you have to force it to keep an electron. It'll just spontaneously throw an electron off. So it's the lowest ionization energies are in that bottom left corner. They're actually negative. We actually can't really measure them because they're so unstable.
Where do you find it?
Don't really. It's considered a rare earth metal. So you find it in really heavy metal deposits. So same place that you would find like uranium and stuff like that. But it's not like it's not found in like anything living. Most of the elements from the 4th, 5th row and up, you can find in trace amounts in living systems doing something somewhere. Cesium not really present anywhere naturally.
So for like the really large atomic number, like radon, anything below that, like on the right side, is it just so big that it just, even though it's like the attraction is large, it just falls apart either way?
So the nucleus falls apart, but if the nucleus is still stable enough to stick together, the electrons will still be around it. So radon still wants to hold on to its electrons, but it's easier to take an electron away from radon than it is from, say, argon, that's in the same column but further up. Does that make sense? Because we're also still kind of neglecting the fact that all these radioactive elements, the nucleus itself can fall apart too, and that changes everything. We're just kind of ignoring that.
Okay.
All right. The last periodic property is worth talking about because it's not one I'm going to ask you about on the test, because it's really kind of hard to define. Metallic character is actually a combination of a bunch of properties. When you think of a property of a metal, what do you think of?
Like malleable.
Malleable. What does malleable mean?
It's absorbed.
Soft, absorb shock. Basically, malleable literally means you can pound it flat. I think I mentioned it when we talked about gold, right? In the gold foil experiment. Malleable literally means you can hit it with a hammer and make it thinner. Metals also tend to have really high, I'll phrase it differently. Not necessarily melting. Melting points is tricky. It depends on what we're comparing it to. In terms of the raw elements, yeah, metals are a little higher in melting point than some of them. But that one's not even predictable either. The one I was gonna say is ductile. Anybody know what ductile means? It's also related to being soft. Ductile means that you can stretch it out and make a wire out of it. Basically, you can either just like push it through a mold like Play-Doh to make a wire. I think that's literally how they make copper wire, is they literally put a vise on it and push it through a little narrow hole. And you get copper wire out of it, just like Play-Doh, just with more force. So that property of being able, but the other way you can do it is you can literally grab both ends of it and stretch and make wire out of it if something is ductile. Metals tend to be ductile. They tend to be malleable. What other properties do metals have? How do you know if something looks metallic?
Oh,
It's shiny. Shiny is actually a metallic characteristic. And all of that comes down to ionization energy. Things that have really low ionization energy have really high degree of metallic character. So actually the bottom left corner of the periodic table is actually where you find the most metallic metals. But we don't use barium for making wire. So electrical conductivity, thermal conductivity, they all factor into this as well. But barium, you would think, would be pretty metallic then, right? But we don't use it to make wires or anything like that or make circuits, because some of the other properties of metals are that they give away electrons really, really easily, which means they oxidize really easily. Has anybody ever done any taken class on computer engineering or done any sort of wiring circuits, anything like that? A little bit. Do wires work when they get oxidized? No. So even though like francium would be a really, really good electrical conductor, it would be really, really easy to work with. You could actually shape it into a wire by hand. However, it's so reactive that it would actually spontaneously oxidize and you just get something that's not conductive anymore. So the metals that we tend to use in making circuits and the metals we tend to use in making jewelry or coins, they're not actually the most metallic. They're the best at staying metal in the presence of oxygen. So copper, silver, gold, to some extent aluminum. We don't really do wiring with aluminum. Does anybody know why? Why we don't use aluminum for wiring? Aluminum is really cheap. It's a lot cheaper than copper and gold. Kind of. It's still just oxidation. Basically, aluminum oxidizes really, really quickly. It just stays looking metallic because the oxide forms a really thin layer, like a skin on the outside, that doesn't let more oxygen through. So it won't rust all the way out. You won't have aluminum rust to the point it gets holes in it like you do with iron. But it also is not a good conductor because it has that layer of oxide on it, and that layer of oxide does not conduct electricity. So they used to use aluminum because it was really, really cheap until they realized it doesn't hold up. It doesn't last long term.
technically, could you use like francium or some of the like extremely like conductive metals in like an oxide, like a vacuum?
In theory, if you could keep it in a vacuum, you could keep it isolated. So maybe like potentially in deep space, you'd still have to keep it shielded because even in deep space, there actually are still molecules floating around in deep space. So you would still have to keep it contained. But in theory, yeah, you could make a pretty low resistance circuit out of some of those more reactive metals if you had it in the right environment. That is pretty cool. All right, we'll end there for today.